Hello everyone and welcome to the 49th lecture of the course Advanced Structural Analysis. We have formulated the geometrically nonlinear problem for the standard beam cases in the last session. Now moving ahead with this lecture, we would like to see the standard analysis approach for these given problems. So we will try to see that what is the incremental load analysis, typically what challenges we regularly face in these kind of problems. Then we will also try to come up with the correction or the iterative approaches, which is one of the standard approach like Newton-Raphson method, and then we will try to see that how does these corrections can improve the overall estimates on these nonlinear analysis cases. So as we continue with the first problem which we have discussed earlier, we considered that there is a truss member on which there is a load which is active. We did the formulation of the given problem in which we reduced the given problem into a simple one element. So we reduced the problem into one element and considered that the single element can be used and we can apply the possibilities of the symmetry to get the response of the overall structure, because whatever the response we will get for this half, the same will be the response for the other half of the system as well. Now in order to get the response of the system, we evaluated the standard equation, which is k of t du bar equal to dp in the given problem. The kt happens to be the tangent stiffness matrix which we have done in a general formulation, and we evaluated kt in the local member coordinates of the given system, which was appearing to be a 4 cross 4 stiffness matrix for the overall problem. From there we also got the procedure to convert the given member stiffness into the global stiffness values by the standard transformation rule, which will also give us a 4 cross 4 stiffness matrix of the given system. So in general, du contains the values of the displacement at the nodal points in the direction of u1 and in the direction of x and y, the global directions of the given system. So I can define it as d of u1, d of v1, d of u2 and d of v2. So these are the 4 displacements which we are located at the positions of the two end nodes of the given system. Similarly, the load, the d of p, is also the incremental load which is typically provided at the ends of the members in the direction of these 4 degrees of freedom, and this can be described as d of p1, d of, or I can simply go with d of p2, d of, or say q would be better, q1, d of p2 and d of q2 in the given system. So with this idea, we are able to identify that the kt, which is appearing to be a 4 cross 4 stiffness matrix, was implemented with respect to this vector component and the other vector component of the increment load, and this typically gives us the solution of a nonlinear equation. To get the cases in this particular problem, we realize that the displacements along the direction of u1, v1 are 0. Similarly, the displacement u2 is also 0 for the given system. So there is only one possibility of the displacement which is along the direction of v or along the direction of v2 in the given problem. In the similar case, we also do not have any of the incremental external loads which are active on the respective positions of the given degrees of freedom u1, v1 and u2 in the given problem, which makes it that the corresponding values of the increments in the displacements will be also 0, as the support conditions are restrained for these degrees of freedom. And as far as the loading is concerned, we are only going to provide the external load with respect to the condition of the d of q2, which is the loading direction with respect to the displacement v2 in the given system. So we can reduce this problem rather than the complete 4 cross 4 stiffness matrix into a smaller problem where I am only looking for one coefficient of the stiffness matrix or the tangent stiffness matrix to evaluate the response. I think this is what we did already in the previous session. Based upon that idea, I am considering the standard results which we obtained in that particular example. The k of t was obtained as 50 minus 100 v plus 50 v square plus 0.1 s. You can refer the standard expression which we described in the previous lecture, where we did the problem on the truss part using the geometrically nonlinear formulation. The force which is active on the member S was also evaluated, and that came out to be this value. we realize that this is a function of u. U means now it is having only one parameter of the one degree of freedom, which is v in the given problem. In the similar way, the kt 44, once we substitute the value of s in the function, can be simplified and it comes out only as a function of the displacement terms of the given problem. And finally, we were also able to obtain the force which is in the direction of the given degree of freedom of the system. So, we write it as P4 of the given system, or one can also call it as a Q2 in the given problem, and this force comes out as the 50 minus V minus 1.5 V square plus 0.5 V cube. We realize that this is also a function of displacement field in the given problem. So, what necessarily a user is trying to solve in a regular nonlinear analysis is the solution of this force equation, because this force equation is connected with this displacement field. So, if I just take the derivative with respect to, if I take a small say variation in terms of the d of P4 value of the system. So, I realize that this could be written as del f upon del v in the given problem into dv for the given system. So, this del f upon del v is the same as the tangent stiffness of the given problem. So, we are eventually trying to solve this given part of the problem to obtain the solution of the nonlinear problem. So, to identify the solution, we are looking to identify a path of the general equation which is defined by this particular function, where P of 4 is representing the force and V defines the displacement which is taken up by the given system. So, if we are trying to just draw the generalized field of the given problem, we draw the load displacement relationship which appears something like this, and that is the P of 4 in which is equal to the function of the displacement terms of the given system. Now, of course, this is a function which is not, or this is a parameter which is not immediately known to the user at the beginning. So, some of the parameter of the displacements are also unknown to us, which we do not know at the beginning of the given problem. So, that is why one cannot directly draw the given response of the system. So, in order to now come up with the solution approach of this given problem, what we do, we identify the standard process where we come up with the stiffness at any point of the given system, and we identify that particular stiffness of the given system as we are locating it as k of t 44 in the given problem. So, instead of now taking the generalized case in the problem, because this is the one particular part of the problem in which we describe the system with respect to these 4 degrees of freedom as we initially started with, but now I can just consider one simple problem in which we have considered say the k of t as a tangent stiffness. So, this is the tangent stiffness which we are interested to define. We are looking for one possible displacement variation, and V is that displacement variation in the given problem. We are having one force condition in the given problem, and that is the P of 4 in the force. So, that is why the whole problem which we identified with these subscripts in the initial phase will now be converted to a simplified case where we will just use the P as a force, V as a displacement, Kt as a parameter of the tangent stiffness of the given system. So, at any point of time I am trying to solve now the equation Kt d of V is equal to dP in the given problem, where dP is the increment in the force of the given system, Kt is the tangent stiffness of the given problem, and d of V is the standard amount of the displacement which is unknown to us. So, as a standard case we also realize that k of t itself is a function of the displacement in the given problem. So, now how do we solve this given problem? So, in order to solve the given problem, we start with one very simplistic idea. We consider, so I will start with this given point only. So, we consider at the beginning that somewhere over here the initial point we define, which is say the point 0, the initial point of the given system. This displacement could be 0 as well. So, it could be either 0 value or it could be any non-zero value, but this is the starting point at which we define the value of the displacement for the given system. And if we define the value of the displacement, we also know the value of the force in the given problem. So, I can just substitute the given value in the function field of the force, and that will give me the respective value of the force in the given system. So, if I say that the V value is 0, the force value also comes out to be 0 in the given problem. So, this is the initial value which is 0, 0, but I am calling it as V naught, the initial displacement of the given system. Similarly, at this point I will also evaluate that what is the stiffness of the given system. So, we consider that what is the Kt value at the position of V equal to V naught in the given problem. And once we obtain this given value, this could be considered as the tangent which can be drawn to the given curve and which is passing through the point V naught equal to 0 on the given system. So, if I draw this tangent, now this is the this is how the initial tangent appears in the given system. Now, in order to calculate the unknown value of the displacement of the given problem, we come up with some initial increment in the load of the given problem. So, one must now understand, as we are not trying to solve a problem in which kT is a constant parameter. So, I cannot take a large steps in the given analysis. I have to go with the small steps in which the variation of the kT is not significantly different than the initially assumed constant variation of the given system. So, with this point in mind, we define our first increment in the system and we call it as, say, d of p1 in the given problem. So, as I define d of p1, my load value from the initial value which I say as p0 changes, and I increase this value by this magnitude which is d of p1 in the given problem. And as I increase this value of d of p1 in the load, corresponding displacement can be evaluated with respect to the constant value of the kT stiffness which I have obtained. So, I call this kT stiffness as kT0 in the given problem, because this is defined at the point V0 in the given system. So, with respect to this initial stiffness, the constant stiffness of the given system, I try to locate the increment. Somewhere over here I cross the given line, and then I say that this is the displacement which I have located for the given case. So, as we obtain the displacement of this much magnitude, we realize that corresponding to the given value, this is the first point which we have obtained on the given system. And with this parameter, that so what eventually will happen, we will be evaluating d of V as kT inverse, and kT is in fact at the point 0. So, I am writing it as d of V1 because the first increment, and the kT of 0 inverse into d of p1 in the given system. So, as I do this part of the analysis, I will be getting the first increment value in the given system, and I will call that value as dV1 in the given problem. In fact, as we are doing the first increment or the 0th increment in the system, I will better call this increment as dV0 in fact. So, that this is the 0th increment only, and this load increment value also we can define with the 0th value only. So, this is starting with the 0 value, and we just define the 0th increment in the given load, and accordingly we obtained the respective value of the displacement at the next point, which I call as now the V of 1, and that is equal to V0 plus d of V0 in the given system. So, this happens to be our first point of the given system. Now, as I have reached to this point, what I will do, I will consider at this point the new value of the stiffness of the given system. So, kT will be further evaluated using the standard form of the kT which is known to us. We know the function of the kT. So, using this formulation, I will consider now V is equal to V1, and with respect to that I will evaluate the kT value, which I now call it as kT1 in the given problem. So, this happens to be the new stiffness or the new tangent which is now drawn on the given system. And as I draw this tangent, so I will just to make a difference, I can just consider that this tangent is with a different color. So, this is the second tangent which has been drawn, and now this tangent is corresponding to the value which I am calling as kT1 in the given problem. Now, as I provide this kT1, I will further go with one more increment in the given system. So, let me say that the first increment which I defined, that took me to a load value of P1. The P1 is equal to P0 plus d of P0 in the given problem, the first increment plus the original load, and that gives me the P1 value. From here I will get the new increment which is say dP1 in the given problem, and with respect to this new increment of dP1, I will further come up to a new point in the given system, come down to the given system over here and locate that what is the value of this new increment in the given system. So, this will be d of V1 in the given problem. So, at each of the point I am able to locate now the new point of the on the displacement field, which is the V of 1 plus dV1 in the given system, and I call this point as V2 of the given system. Similarly, the second point which I have defined over here also appears as a point P2 of the given system, and this point P2 is d of P1 plus P1 in the given system. So, as I keep on doing this procedure, at the second point I will further now modify my stiffness value. Rather than KT1, now I will define the KT2 at this point of the given system. So, I will bring again a new tangent on the given system, say with the black line. So, I bring a new tangent, and this is the third tangent of the given system, which is KT3, KT2 in the given system. This has been evaluated, or this KT2 is defined with respect to the value of the KT at V equal to V2 in the given problem. So, as we calculate the individual displacements also corresponding to these displacement values, I can keep on evaluating the respective value of the KT parameter of the given system, and as I am doing this evaluation, I am able to draw a new tangent line on the given system. So, this procedure can be followed to evaluate the continuously defined new tangents on the given system. Of course, now you can see that it is not going to track the given original curve in the exact same manner. Somewhere there is a difference, and as you keep on moving with the curve further, the difference keeps on increasing, and that is how that is what the standard incremental load analysis looks like. We keep on incrementing the load, and with each increment in the load, we define the new value of the stiffness, the tangent stiffness of the given system, and corresponding to that value of the tangent stiffness, we evaluate the increment in the displacement of the given system. Once we have the available displacement with us, we update the value of the tangent stiffness, and again we, with the new tangent stiffness value, we provide the new increment in the given system, and successively this procedure can be followed till we reach to a sufficient distance of the deformation which we want to model in the given system. Now, this is what typically the standard procedure looks like. We have briefly shown here that KT of 0 with dV0 is equal to dP1. This will give us the, say, the first point with respect to KT0 point. We obtain the increment, say d of P0 in the given problem, and this gives us the first point P1 in the given system. With respect to this point P1, I will be obtaining the displacement over here, which is V1 in the given problem, and this V1 will be equal to V0 plus d of V0 in the given problem. As we have obtained the first displacement point, we further go with the evaluation of the new tangent stiffness, which is evaluated at this particular point. So, I will come up with the KT1, which will be evaluated as KT with respect to V equal to V1 in the given problem, and again we give the further second level of increment in the given system, and that could be defined with, say, dP1 in the given problem. With this increment, we reach to the new position, which is P2, and corresponding to this P2, we obtain that what is the displacement in the given problem. So, this happens to be the second displacement, which we call as V2 in the given problem, and this is the increment which is identified as d of V1 in the given system. As we come up with this second value, we further go to the system and identify the third tangent stiffness in the given system. Now, as we do with the third tangent stiffness, we come up with that value, that KT of 2 in the given problem, and subsequently we can continue this procedure. So, at any point we can now write the generalized expression that KT of I is equal to the KT with respect to V equal to V of I in the given problem. So, this is how we are evaluating the stiffness, the tangent stiffness in the given problem. So, if I am at the position of the given point over here and evaluating KT of 2, I am locating it with respect to the value of the V2 in the given system. Similarly, the standard incremental stiffness expression can be written as KT of I into dV of I equal to dP of I in the given problem. So, with respect to any given increment in the load, a number of the increment, ith increment of the given system, we will be getting the ith increment in the displacement with respect to the ith tangent stiffness of the given system, and this will be updating the value of the displacement field in the system, which we write as V of I plus 1. So, the next displacement value will be obtained as V of I plus 1 as V of I plus dVi in the given problem. So, once we are able to do this part of the algorithm in a successive manners, we will be able to identify the overall load path, which is not corrected, but which is evaluated with respect to the tangent stiffnesses being evaluated with respect to the increments in the load values. Now, we will just go with one simple problem statement so that we understand that what is the utility of the overall method. So, as a similar case, we have defined that what is the tangent stiffness value, which is defined by the function in terms of the S. S value is also evaluated so that we know the value of the internal member force in the given system. These values have been again adopted for the same problem which we started or which we defined at the beginning. So, first we start with the 0th step, which is, as we see over here, that we start with the initial displacement value being 0, and corresponding to that we define the stiffness of the given tangent stiffness of the given system. So, if I go with this part, I call it as the 0th step. So, the idea is that somewhere we are starting with the first value, which is with the 0 parameter. So, that is why we call it as the 0th step in the given system, and as we go with the first value, we will go with the first step. So, each time we are able to define the stiffness or the tangent stiffness value with the same order in which we are doing the increment in the system. So, with the 0th step, if we go with, we first evaluate the KT value, which is the KT 0 in the given problem. The KT 0 happens to be the KT with respect to V equal to V 0, and I realize that the V 0 value is 0 in the given problem, which we have considered. So, based upon that, the value of the different parameters, I can calculate first the value of S. So, S naught comes out as 0, because as the V will be 0, so S will also become 0. We call this value as S naught. Similarly, the KT can be evaluated based upon that KT 0, and as the S value is 0, we get the overall value of the KT as 50 in the given system. Once we have obtained this value, we will go with the available set of increment which is provided. So, as per the say provided condition, we want to go with the first increment value of 0.4. So, as you go with the 0.4 increment, you will write the condition as KT of 0 into dV 0 in the given problem, which we want to evaluate, which is unknown to us, into d of p in the given system. Now, d of p is something which is the increment condition and which is defined in this case is 0.4. So, if I substitute the given value, I get to know that dV of 0 is equal to dP upon KT 0 in the given problem. In this given problem, now we have only one parameter of the stiffness, we are evaluating only one parameter of the load and only one value of the displacement. But we must not forget that in general the procedure is prepared such that the value of the KT can be a generalized matrix, the d of u can be a general vector of the given system, and d of p could also be a general vector of the given system. So, there could be more than one loads which are active in the given system. We can have the increments in the load in a same manner or a different manner according to the given situation, and according to that we can have the analysis of the overall system. What it essentially means is that if we consider a general case where, say, a member, truss member like so, if we consider a case like this where there is a truss member like this, which is subjected to, say, the multiple loads, one over here, second load over here in the given system. Now, this member does not have any symmetry. So, one has to analyze it in the full conditions. So, based upon the available set of displacements of the given problem, one will come up with the KT into du bar equal to dP, this kind of expression. In fact, I should not say u bar, because now all of these expressions will be defined in the global coordinates of the given system. Now, what the user will do in the given problem, there are different positions which can be provided with the external load. So, if I say that in the given system we have this value as P1, this value as P2 in the given problem. So, the given increments in the system, say dP1, dP2, or if there are any other increments in the system, say dP3 in the given system, they could all be either provided with the same magnitude, which means that I can have, say, the dP1 value is also equal to 0.4, dP2 value is also equal to 0.4, and dP3 is also equal to 0.4. Or in most of the cases, what we typically do, that whichever effect we want to primarily look to reproduce, or primarily we want to investigate, we concentrate upon that particular value. Say, if the P1 value is the primary concern for the evaluation, we consider this value as 0.4, whereas the dP2, the second value, will be just provided with some factor value of the P1 load. So, the lambda becomes a factor which could be either very small or very large based upon the given conditions of the system. So, in most of the situations we have not only a simple single value of the given problem, but we could also entertain in the similar way the problems having the vector identities in the given system. So, with this idea in mind, we now have a clear evaluation that can give us the displacement at the first node or the first iteration of the given system. So, I got to know that dV naught is equal to dP, which is 0.4, divided by the kT naught, which is 50 in the given system. So, in all those cases where kT happens to be a general matrix rather than the single value, this will be undergoing the full inverse of the given system. So, with this part we evaluate the first value of the system, and as we evaluate we get the V1 is equal to V naught plus dV naught in the given problem. Once we have evaluated this part, we go with the first step in the given system. So, this was the 0th step. Now, we can go with the first step in the given analysis. As a part of the first step, what a user can do, I can evaluate the kT1, which is now evaluated as the kT value with respect to V equal to V1, and as I evaluate this value, I can, corresponding to this given value, I can evaluate now the dV1 value in the given system, which can be calculated as the increment in the given load, which is say now defined with the value of 2 units. So, dP1 divided by kT1 of the given system. So, this way we can do this process in an iterative manner for the multiple steps. We will briefly try to show some of these steps so that we can verify the results. So, as a first step, we evaluated the kT value equal to 50, S naught comes out to be 0. We have dP value which is 0.4, and based upon that we got the dV naught as 0.008, and V1 comes out as 0.008 itself, because V naught value is 0 in the given system. With this part we move to the first step in the given system. The first step, we evaluate first the S1 value, we substitute the value of V1 which we evaluated just now 0.008, and we substitute into this expression of the S, that gives us the value of S1. We substitute this value of S1 and the V value of, so V1 value we are writing over here at 0.008, and we substitute this value of V1 into the kT expression, which gives us the kT value as 48.8048. So, you can also realize that as the value of these steps are increasing, the value of the stiffness, which was initially 50, is also decreasing. So, we are having a decrease in the stiffness as the displacements in the system are increasing. So, this value of the stiffness has been evaluated. Now, we can evaluate the dV1, the second displacement of the given system, and that can be done with respect to the increment, which is 2 units, divided by the kT of 1, and that comes out as this particular value. So, this is the value of dV1. Based upon that, I can calculate what is the V2 value, and this is V1 plus dV1 in the given system. So, once I have obtained the value of V2 in the given problem, we will substitute this value of the V2 to obtain the value of S again. So, what we will do, we will just put this value V2 is equal to 0.04898, yes, and with this value we will substitute the given expression into the S expression, and we get the value of S2 now, which is 23.89. From this S expression and the value of the displacement, we get the kT value in the given system, and then finally we do the similar process to obtain the V3 in the given process. So, these are steps we can successively do. We suggest that you can go through this part of the tables and try to check whether these answers make sense to you. And with that part, now once we are comfortable, we can now go ahead and check that what happens to the given response in terms of the force comparison. So, what we have seen at the beginning, that other than the value of the kT and the S parameter of the given system, we were also knowing the value of the initial function f of the given system. So, f or the function p for the given system was also known to us, so which is defined over here. Now, this is something which we said that this is the original function of the given system. Now, if I just substitute the individual values of the displacement which we just obtained, like the value of the V1 which is 0.008, value of the V2 which is 0.4898, value of the V3 in the given system, then we can also substitute these values of the V in the initial function which was located over here, and corresponding to these initial function, what we will realize that if I substitute the value of the V equal to the first value 0.008 in the given problem, it will give me the first function of the given system, which is say f1 in the given problem. And with respect to this value of the f1, now what I can compare, I can see that whether this value of the f1 is same as the value of the increment which I have provided in the given system. So, if you realize that as you are providing the increment value of 0.4, the value of the load is 0 at the initial point, at the first step it becomes 0.4. So, if I really get the value of 0.4 itself with the given analysis also, that means the curve which we are trying to obtain and which is somewhere like this, we are somewhere able to track each and every point of the given curve. But necessarily if you now look at the answers, you will realize that when we put the V naught equal to 0, the first value, it comes out to be 0, which is very same, both of the points are similar. When I go with the first point, we realize that the value of f of V1 comes out as 0.3952, which means that the force value with respect to the original function or the original force field at the value of V1 is equal to 0.3952, whereas the increment value has been provided the value of 0.4, which means that at the same position the V1 value is provided by the formula or by the given curve as 0.4. So, if I define this value as 0.4, I say that this is the point which we are locating in the given system. Similarly, if I go to the V2 as the second value, I define the V2 value in the given problem somewhere say over here, and with respect to V2 I get the force value as 1.9248, which is the force value on the actual curve, whereas if I take the value of V2 with respect to the increment in the load, I realize that the value is 2.4 in the given system, which means that the value of the actual system for the same V2 parameter will be somewhere located over here. So, this is the point which we have obtained for the given system. Similarly, I go to the V3, which is the third value of the given system, and corresponding to that I get the force value which is somewhere on the real parameter of the system, and that value comes out as 4.6147. But if I now look at the value which is actually there in the given system for the third point, it is 5 units, which means that the actual curve and the same displacement value of V3 will be located, not the actual curve, but the provided curve with respect to the given value will be giving me a value of 5 units in the given system. So, you wanted to get this curve, but somewhere you are ending up with the if I show with a different color. So, this is the point we started with, and now we have got the system which is connected with these points. So, there is a error which is typically existing in the given values, and we realize that there is a difference between the force which is actually appearing with the given problem and the actual force of the given system, and which we need to correct in the given process. So, with this we will try to come up with a procedure where the each increment is going to produce the value which is having the larger parameter, but now we will try to correct it with respect to the actual value of the force field which is available in the given system. Once I am able to correct this value, I will try to come down to the same position on the given curve. As I continue with the given next value, I will further correct it and try to come to the given system, and this way we will be having a procedure in which the each increment of the system is also provided with the number of iterations such that the force values are not only taken as the final value at the beginning, but they are further corrected by using the simple equilibrium conditions to verify the results more accurately. With this we stop over here, and we will continue with this part in the next session. Thank you everyone.